Good morning, good afternoon, good night, wherever you are in this globe. So thank you very much for coming to this talk on how to design and how to improve the efficiency of RF to DC converters. My name is Nuno Borges Carvalho. I'm working on the University of Aveiro and on the Telecommunication Institute, which is a research lab in the University of Aveiro in Portugal. And during this talk, I will show you how to design from a hardware perspective and also from a signal perspective the best waveforms that you can actually implement to improve the RF to DC efficiency.
Okay, so the talk will be divided in the following 3 points. So initially, an historical introduction and current trends in wireless power transmission. We'll now, after that, we'll look to the wireless power transmission link design, and then we will address a little bit of energy efficiency, far field wireless power transmission developments. Well, let's start with the current historical introduction and current trends in wireless power transmission. And if we have to talk about far field, or let me say long range wireless power transmission, we should go back to, let me put it, the Greek history time, where they only, and at that time, they actually start to see that if you rub a piece of hammer, that piece of hammer can attract certain things. So there was a force that was not explained by gravitation, but that was a force that can actually move and can create some attraction between two bodies that was a little bit unknown at that time. Well, then after several years, a significant number of years, William Gilbert actually showed one of the first devices called the electricus that actually showed that there was a magnetic field and that you can actually have a device that point to a certain direction. So it was like an invisible force that was around it. Those initial works allow several years later a very important person called Maria Ampere to actually show that if you have a current traversing a wire, that current can create a magnetic flux around that wire where it is flowing. This was further explored by Faraday's law of induction, where it says that let me put it this way, electromagnetic force can actually be created around or can be used if you are within a variable magnetic flux environment. So if you have a very magnetic flux, and if this very magnetic flux is covered by a wire around it, you can actually use electromagnetic force within this wire. So these initial concepts actually allow later on in around 1864, the combination of the electrical field and the magnetic field by using or by a very important person called Maxwell. And Maxwell actually was one of the first persons that, from a theoretical point of view, show up that we can actually have an electromagnetic wave flowing in the environment, that this electromagnetic wave actually, when it flows, when it is transmitted, it can actually create the amount of power. So if you have to say who is the father of wireless power transmission, I will say Maxwell is actually one of the first persons that show you that we can actually create this electromagnetic force that moves towards the environment. Well, later on, Poynting showed, and using the Maxwell equation, showed that there is a flow of power across an area on that as electromagnetic radiation. And so we know quite well the Poynting vector that somehow corresponds and somehow is related to the field. Let me create here. So the Poynting vector is actually related to the field of the magnetic field multiplied by the electrical field. So this was actually the first theoretical aspect where you show that you can send power energy via electromagnetic waves, and this is actually the basis of our wireless power transmission as we have it today. Well, Hertz in 1888 showed a little bit, or gave a step further by showing that this theory is not really only a theory, but you can actually relate this theory to an experiment, and he showed for the first time that you can transmit energy over the electromagnetic field. That is, at that time, he actually called this electromagnetic field the black light. So it was like you are sending energy over something that you don't really see, but you are sending energy, and that energy can be converted into force. So by saying this and by having this experiment, later on, Tesla came up, and by so many things that Tesla has implemented, so many things that Tesla has done, Tesla has actually showed that we can transmit energy using radio waves. And Tesla has a dream, and the dream was I should send electromagnetic waves to the atmosphere, and those electromagnetic waves should be collected by antennas all over the place and power up my house, power up my devices, power up my cars, and so on and so on. So with the London Cliff Tower project, the idea was actually to be able to distribute energy over the world using only electromagnetic waves. Well, this actually, we normally, from the far field aspect, we normally attribute this wireless power transmission concept to Tesla, but if you look carefully, this actually goes back to Maxwell, Faraday, Ampere, Hertz. So all these scientists was actually the beginners of this amazing theory. But only around 70 years later than the Tesla has shown that it is possible to transmit energy via electromagnetic waves, only 70 years later, William Brown actually pioneered what is called the microwave power transmission. And the microwave power transmission, he also give the name of a very important device in this technique, in this technology, which is called the rectenna. So the rectenna is nothing more than a device that actually will collect this electromagnetic wave, will convert the electromagnetic wave back to DC, and will allow us to power up other devices. So the first experiment that William Brown used was mainly to power up an helicopter. Well, it's not really an helicopter. If you look at the image, it's mainly an antenna connected with an hélice, but actually it was like an helicopter if you want. And the experiment was quite successful. So you have a microwave generator, you have a reflector, a huge reflector, you power up your energy to this reflector that creates a beam. And this beam has a focus nearby. Actually, the focus was a little bit in the between the reflector and our receiver. But the idea was to power up this structure that has an hélice around. And if you can see this in this figure, so you have the reflector in the bottom, you send the beam to this device, and the device was actually connected with a cable so that it doesn't fall. But when you have the energy being supplied to this antenna, this antenna, let me put it this way, this creates the hélice to move, and you have a flying helicopter without any energy on board. So the energy was beamed by the ground. So as you can see, I start by saying that we start this amazing adventure before 1600 before Christ, let me put it this way, and only 1960 we have some preliminary results that show us that this is viable. Well, then after that, a lot of other activities came on. So in the 80s, Canada Communication Research Center created a small airplane where they have an antenna similar to Brown that you can power up and you can fly with it. In 93, there was another experiment in Alaska. In 2001, there was the possibility to transmit a huge power beam from Iceland to Iceland, so power up the small cities. In 2008, there was a first demonstration of how to transmit energy over 148 kilometers in Hawaii. So all these experiments actually allowed the society, allowed the world to see that far-field wireless power transmission is possible. It has a lot of problems, as you will see, but it's possible to do. And of course, with the advancements or the recent massification of what is called the Internet of Things, we start to think that actually wireless power transmission is a key element in all of our future developments and all our future gadget developments. And why is this? Well, the thing now is that we are expecting that IoT devices with the 5G advancements that we have been looking carefully recently will explode in terms of number of devices. Well, but if we explode in numbers of devices, if they are battery powered, the amount of batteries that we need to operate these IoT devices is huge. It's so huge that we should come up with a different paradigm. We should change our paradigm, how we power up these IoT devices. The good thing about this is that really the economic part of IoT will increase significantly also. So we are expecting that a lot of companies, a lot of research is done around IoT so that we can actually make it viable, make it financially reasonable, and implement IoT sensors all over the place. So this is really what I have here. So the number of IoT devices will explode significantly, and the number of applications of this IoT is huge, significantly high. So one possibility is really to use wireless power transmission and use wireless power transmission to power all these IoT devices. Well, on the other application, and a very interesting application is what we call now clean energy, or if you want, space power satellites. What it is? Well, it's mainly to get or to collect energy out of space and bring that energy to ground. So create a beam of energy that can actually increase the efficiency of our solar panels since they will be outside of the atmosphere, and then create a beam that can power up these beams or can power up these large arrays in the ground. And this can be used for Earth, so that as an alternative to fossil energy, or it can be used to power up small drones, to power up small, let's say, groups of based moon stations or Mars stations, so that we can do space exploration by using power beams in certain occasions. And if we go for space applications, well, the applications are huge. Remote space probes, planet explorers, space probes to monitor the health of your satellite or of your space probe, remove the cables of those sensors. So there are a multitude of wireless power transmission applications in all of these devices, in all of these approaches. And by the way, I can show you that recently the Naval Research Lab, with an astronaut on board of the space base, was actually show from a very simplistic approach how you can collect energy even inside the space station and power up a small LED. So they call it the lectenna. This is mainly a steam analysis of how can you build a very simple demonstrator of wireless power transmission. So the video of the astronaut showing that it's possible to collect energy inside space station from electromagnetic waves is online and it's available, and it's very interesting to see if you are curious enough to go there. But there are other applications. So NASA, here I'm showing you the rings from NASA. They actually show that they can have some systems based on electromagnetic based propulsion that can monitor the health of your base station. And sometimes you could reduce the number of times an astronaut goes outside space station to monitor the health of space station, and you can use some of these solutions to actually grow around the space station and monitor the space station. So this shows you that the amount of applications of wireless power transmission from an electromagnetic point of view, or if you want far-field radiative point of view, is enormous and is there so that you can actually push it up and discover important approaches to that. Well, in my university, in my research lab, what we are trying to do is really to combine the concept of the Internet of Things and move this concept to the space. So move the concept of the Internet of Things that we have already in the ground. Most of them are battery operated, but we want to move these to space exploration and not having it battery operated. So remove the batteries out of it and create, let me say, batteryless sensors that go around and that can communicate with a low orbit satellite that could be as close as 5 kilometers, 6 kilometers. So this satellite will be responsible for powering up all the IoT sensors on the ground and then send information back to a ground station in Earth so that we can monitor all these solutions. Well, wireless power transmission is also being looked from another and different aspect. As I will show you, wireless power transmission demands that you have a transmitter and a receiver, so similar to a wireless communication link. In the wireless power transmission, we could, in certain situations, not have the transmitter. And normally we call this the electromagnetic energy harvesting. What that means, it means that we already have transmitters of electromagnetic around. So you have antennas that are being broadcast electromagnetic waves. You have Wi-Fi, GSM, digital television. Why not collect that energy? And why not convert that energy back to a small amount of energy that can power up small sensors somewhere? So when we don't control the source of the energy, we don't call it wireless power transmission. We normally call it electromagnetic energy harvesting, because really what we control is how to harvest that electromagnetic energy, not how to produce that electromagnetic energy scenario. Well, let's now see how can we design a wireless power transmission link. Well, a wireless power transmission link is much like it is shown here. You have a generator, a source of energy that converts DC back to RF, to radio frequency. We normally have an amplifier to increase the power of this RF energy, or sometimes we combine these both in the single device and we call it power sources, so that the generator is combined with the amplifier. Then we normally have an antenna, and this antenna normally is an active antenna array. Why? Because we want to create photons or beams of energy with very high gain, concentrated beams of very high gain. And then on the other side, we have another array that will collect that energy, and that goes through a diode, or most of the time it's a diode, it can be a transistor, it's really a rectifier. So it's a device that converts RF, radio frequency, back to DC. And sometimes you need a DC to DC converter so that you have enough DC voltage to power up some of your devices. So what is the problem? The concept is quite generic, quite simple. What is the problem with this scenario? Well, the problem is that the DC to RF efficiency is not 100%. That means if I have 10 watts of DC, I will probably not have 10 watts of RF. Probably I will have 6, 7 watts of RF. And the other 3 watts are dissipated in it because of the process to actually generate the radio frequency scheme. Then we normally have the amplifier, and if you have the amplifier, you have another efficiency on RF to RF. conversion. What that means again, you have 1 watt that goes into the amplifier. The amplifier gives you 500 milliwatts because the other 500 milliwatts are lost in the translation, let me put it this way, are lost in the conversion from RF to RF, and most of the time is dissipated via its waves. Then we have our antenna. Unfortunately, our antenna is not 100% efficient. Again, you have losses on the antenna. Then you go towards the, let's say, the link, the end interface, and there it depends on if you are creating beams, if you are creating focus, so you lose a lot of power when transmitting. Then you have an antenna on the other side again, not 100% efficiency. Then you have your RF to DC converter and your DC to DC converter. Well, again, not all these devices are 100% efficiency. So this is the big problem in far-field radiative wireless power transmission. That is, if you calculate the DC from one side to the other, so the DC to DC conversion, the efficiency is very low. And mainly it's very low because if you multiply all these efficiencies, even imagine that all efficiencies are 90%. Only on the transmitter, if I have 90% and 90%, these two efficiency will be 81% because they multiply. And if you multiply again by 90%, it goes to 70% and so on. So the DC to DC efficiency is extremely low. And this is something that we have to overcome. So how do we overcome this overall efficiency? How can we maximize this overall efficiency? Well, by maximizing each block independently. So we have to maximize the DC to RF efficiency, we have to maximize the beam efficiency, including the antennas on the transmitter and receiver, and you have to maximize the RF to DC conversion efficiency again. And of course, if you look to the antennas, there are a lot of losses on the antennas, not only on the air interface, but also on the polarization that you use for your antenna. So it's a huge problem. So this is something that should be carefully think before we actually build a wireless power link. And if you do a very simple calculation, so here I show you simple calculations making this table where I create the different frequencies. So I'm using different frequencies. They will give way to different wavelengths. Then I'm assuming DC to RF efficiency that goes down as you increase efficiency because this is known. The transistors do not behave well, or let me put it this way, the characteristics of the transistors degrade as you increase the frequency. Then I'm assuming that I'm transmitting 100 watts in all these links. I have a 30 dB gain of the amplifier. I have an RF to RF efficiency around 70, 60, 40, and 30%. And so this is the power that I'm feeding the antenna. 60 watts on the transmitter, 45 watts, 26 watts, and 18 watts. Then I play a little bit with my beam efficiency. So the antenna gain, the distance, this will give you an antenna gain of 20 dBs. I'm assuming again a 20 dB antenna gain on the receiver and a distance of 2 meters between both of them. So if you do these calculations and then you calculate this is wrong, sorry, this should be RF to DC conversion. So if you go, you see that depending on the frequency, depending on the distance, actually the DC to DC efficiency is quite low. And this is something that we have to think, that how can I improve the efficiency of each one of these components? How should I improve the DC to RF efficiency, the RF to RF efficiency, and the RF to DC efficiency? And let me start briefly, and I will not spend here more time because I will talk mainly about RF to DC converters, but how can we increase the DC to RF efficiency? Well, we can increase that efficiency by designing better power amplifiers. So better power amplifiers mean that we should operate power amplifiers in a switch mode configuration so that we can make it like a CMOS gate. If you look to the digital circuits, before we used to use TTL approach, recently we use CMOS mainly, and the CMOS allow us to actually create digital circuitries that consume so low amounts of power. So why not bring that theory back to the RF amplifiers and increase significantly our efficiency? So this is something that we have to look carefully. As I said, it's not the topic of the discussion today. Well, then we have the beam efficiency. In the beam efficiency, you can do several things. We can optimize the antenna size and beam control so that we work in the Fresnel zone, so we don't go to the far field zone, because if you go to the far field zone, you lose completely your energy. Fresnel zone does not mean close range. It can be long range, but continue to be in the Fresnel zone. Well, we can try to design a different beam, not spread all the power everywhere, so try to focus my power. This is really what we try to do when we design, for instance, Gaussian beam antennas arrays. We can use the reflectors or antenna lenses so that you can actually improve your focus of your energy in a specific size. So this is something that we should also look carefully when designing these links. Again, I will not focus on the antenna in this presentation. Well, this is an example of something that you can do. So this is a antenna array, you have a reflector, and you can actually send this power over the air with the reflector. You can increase the gain significantly. And one of the things that we normally use in the transmitter is that instead of creating a single amplifier that will feed all the array elements as they are presented here, we can change this amplifier by individual amplification. So each one of these cells will become a transmitter with his own power amplifier associated. So these are this is an example. So you have your transmitting antenna there. You have individual elements here transmitted, and this is actually a power amplifier that we developed with this group of companies within an European project called GANSAT, where we actually developed a power amplifier that is so tiny that you can actually go to your antenna. So let me go back. You can go to your antenna, you can feed each element of the antenna individually so that the overall power is obtained in the space and not before feeding the antenna. So the antenna will be fed by individual amplifiers in each point. Well, then you go through your beam and you receive your signal. What is the problem of receiving the signal? Well, first, you should guarantee that you have a precise alignment of your transmitter and your receiver. This is mainly for polarization. Well, you can use circular polarization, but you lose a little bit when you use circular polarization. So we try to use dual polarized antennas. Why? You can say, okay, but why not aligning the antennas on both sides? But the problem is that if you want to do this for IoT, you don't really know if your sensor is going to be aligned with your antenna or if your sensor is going to be completely disaligned with your antenna. So actually what we propose in that situation is instead of using circular polarization, use a dual polarized antennas, and instead of having an RF to DC converter, why not have two RF to DC converters that actually will create two pairs of RFs of DC power or DC collectors, let me put it this way, and this way you can maximize all the time your energy on your receiver. Well, actually, this is the antenna that we designed. We have matched each one of the elements, so this is for horizontal and vertical solutions, and this antenna will be then will feed different or two RF to DC converters in each one of the polarizations. Well, and if you look to the RF to DC converters, the RF to DC efficiency is extremely low, as you can see. So you see that if you increase the amount of power that you fed your rectifier, you can achieve quite good values of efficiency. You can go up to 90%. There are already results in the market there. But if you look to the Internet of Things scenario, where actually my device is quite far away from my transmitter, and my device is a low power device, most of the time The amount of power that arrived to my IoT device is around -10, -20, -30 dBm or even less. And if you look here, what you see is that the efficiency of RF to DC converters here are quite low, and these are the ones published in the commercial in the some of the publications that we saw. And what is an RF to DC converter? Well, as I said, an RF to DC converter is mainly a rectifier circuit. So it can be a very simple circuit like here, where you have a diode and you have a DC filter afterwards. So your diode will rectify your signal, or you can have a multiplier so that not only you have a DC conversion, but you multiply DC, so you have a higher DC voltage at the output of your device. And as you can see here, well, if the input power levels are around 10 microwatts, this means that the efficiencies are very low, 10 to 20%. And if you increase input power, the efficiencies can increase a little bit. And this is really what we have to see to do. How can we increase this RF to DC conversion? By the way, if you want to actually pick up one of these diodes, if you explore these diodes instead of using the traditional diode model, if you expand this, you'll see that the output of your diode will be a DC component, a component at input frequency, second harmonic, third harmonic, and so on, because it's a highly nonlinear device. So when we design one RF to DC converter, we need to consider what is the power source, that is what type of antenna I'm using, what is my matching network that will feed this power to my nonlinearity. As I said, here I will use a diode as nonlinearity. And then at the output, you normally use a low pass filter to eliminate fundamental, second harmonic, third harmonic, and so on. So you get only the DC component. And if you look inside the diode is a complex structure. It normally has some parasitics. It normally has nonlinear current here. Well, you can represent it by nonlinear resistor if you want, a nonlinear capacitor. And as you know, the diode equivalent model of the diode is normally given by the Shockley equation, where you have your saturation current and you have your VT and so on. So this is really the operation of your diode. So the operation of your diode is mainly an exponential function with a breakdown. So if you increase a lot the negative voltage, you'll get to a breakdown situation. And if I excite my diode, a simple circuit like it is here, if I excite my diode with this, let me say, sine wave, what is going to happen? Well, the diode will auto-bias. This is the first thing that will happen. And then at the output of the diode, you'll have this voltage, this halfway rectification voltage, that after it goes to your output filter, you do an average of this voltage and you get your DC component. So your DC component is here so that you can have the DC component. Well, how can I increase this efficiency? Well, one simple example is you can actually use a diode where this VT, so this, let's say, mean of this voltage, where the diode goes up, it is zero. Unfortunately, you don't have on the market any diode that has a zero voltage, is very low. You can use Schottky diodes, which have a VT that is quite low, but not zero. And so what that means, it means that you need a little bit of energy to allow the sine wave to go through this knee and start rectification. And this is the main reason why for low power devices, so for low power or low amount of input energy on your antenna, you really need to overcome this need so that you can start rectification at this point. So how can we actually design this using a circuit simulator? So normally what I recommend is that you use a diode, you use a good model of your diode. This is something that sometimes is not available. If it's not available, you have to come up and you have to get all these coefficients for your diode. So what I recommend for students is get a diode that has a model already available on the market. Let me put also a parenthesis here. Sometimes these diodes have a model on the market, but models are not very good. So it's a little bit tricky. So after you have this model, you use it here. And normally I use what is called a large signal S parameters. Why? because I want to match my antenna, which is represented here by the source, to my diode. And if I want to match my antenna to my diode, I should guarantee that I know the input impedance of my diode, so that I can calculate the complex of that input impedance. So I have a maximum energy transfer between the antenna and my diode. And what happens is that the diode is a nonlinear diode. So the impedance, as you saw when I show you, let me go one, when I show you the equivalent of the diode, it has a nonlinear capacitor here. What that means? It means that depending on the power that you have here, the capacitor will change. And if the capacitor changes, your impedance changes. And so your matching network is no longer a good matching network. So instead of using traditional scattering parameters to actually identify my diode, since it is a nonlinear device, I normally use large signal scattering parameters, so that you can actually extract scattering parameters for the input power that you are expecting to have at input of your diode. And by doing that, you can actually go, you extract this input matching network, large signal matching network for a specific voltage at the input, and you can design your input matching network actually to fit this specific impedance and not another impedance. So what is going to happen is that you can tell me, and then if I change power, well, if you change power, you need another impedance. If I change down or you change up, probably the input matching network should change. So what we normally do, we select the number of powers we want our device to work. You measure scattering parameters in all of them, and we normally do an average, because at this moment we cannot tune the input matching network. We are working on that in my lab, but at this moment our matching network, I will consider in this case that is a passive matching network using capacitors, inductors, transmission lines. So it's fixed. So we normally do an average between all these devices. And by doing that, we can actually optimize my input matching network. Well, at the output is the same thing. I need at the output to get rid of all fundamental harmonics and so on. Why? Because they are spending energy. I don't want them to be spending energy but in it. I want them to be converted back to DC. So one thing that we can do at the output is not only design a very good low-pass filter for the DC component, but we also have to design carefully structures that can do what is called harmonic rejection. So we can tune the harmonic so they can go back to the diode and increase the DC a little bit more. So we can send these harmonics back to your diode to actually be converted again back into DC component. And this is something that we have been doing. So these are some of the examples of the scattering parameters that we did on the rectifier circuit and how we can implement that. And this, at the end, will give you the correct numbers of the capacitors, inductors, and resistors to design a correct RF to DC converter. Well, but as I said before, we have a problem because we have to overcome this need. And the matching network will not overcome this need if you have a low power. So how can I go to the need faster with the same output average power? So we came up with an idea that why we are using a sine wave. Can we use a different waveform so that we can go to our need faster with the same average power? So we came up with this waveform. This is really what it's called a multisine. So it's an addition of sines. So instead of having one side, I have 1, 2, 3, 4, several amount of sines, and we synchronize them all together. What that means, since we synchronize them all together, we can create peaks of voltage with the same average power. What that means, it means that I have a huge amount of voltage, so I can excite my rectifier harder than I was exciting before. So the output is going to have higher peaks, and the average of the output, is the DC, will go up. So for a simple scenario, you can actually increase a lot of RF to DC converter. Here I have an example. So I have my shockwave equation. I can approach this with a tailored approach. And if you do it with a tailored approach, you can actually see that if you excite your sine wave with a cosine, a simple sine, you have the DC component is something like this. This is the second harmonic, and this is the fourth harmonic. So actually, I want to filter this out, or let me put this, I want to actually terminate these harmonics so they can go back to your diode, and I want to extract this DC component. But then what we found is that if we pick up this let me say, if we pick up, not this, sorry, let me go back. If we get this equation, and instead of using a sine wave, we use a summation of sines. Here I'm using 4 sines. And if I go through all the arithmetics and all the trigonometric equations, I see that the DC component is something like this, which is very similar to what I had before. But now I have another coefficient, and the other coefficient is this one, and it's related to the phases, to the individual phases of each one of my sines. I'm assuming all sines have the same amplitude. So if I have different phases, what this tells me? Well, tells me that if I choose carefully these phases, I can increase the DC, so I can increase the output DC, and thus I can increase direct to DC conversion. Well, the trivial solution for this is to have all phases equal to 0, because if all phases are equal to 0, all these cosines will be 1, but there are the other options also. And sometimes having all phase aligned is not very easy because you have to go with all these signs through your beam, and sometimes your air interface will change the phases a little bit. So, by the way, if you use 10 tones and these two signals are exactly the same type of signal in spectrum, so if you do the spectrum of these signals, they are 10 tones with equal amplitude, same average power, but as you can see here, if you make a random tones between them, the peak of your voltage will be around maximum 2 volts, but if you synchronize them all together, you can have a peak of 10 volts, so you excite the diode much more. Well, the other problem is that when you go with this signal, I already excite the signal much more, that's good, but then I have a problem with the output. Why? Because the output now not only has the harmonics, but will also have what is called the baseband signal. Since I have 10 tones, they will be moved to DC, and so the DC will have something like this. So this output matching network is no longer a simple DC filter, but you have to guarantee that when you design this output matching network, the low frequency matching network, you should guarantee that your capacitor that you have in your filter here will not discharge a lot. That means that the tone spacing between the frequencies is very important. As close they are, the longer the peak repetition will be. So the more time you need from going from one peak to the other. This allows the capacitor to discharge, and you don't want that. So you want to increase the number of your tone spacing, but if you increase it a lot, then your input matching network will start to have a problem of bandwidth matching network. So this is a compromise between the output matching network and the input matching network. So as I said here, the tone separation is very important, and the lower the tone space frequency, the higher time between peaks, and vice versa. Well, we actually pick up these solutions. This is a 2.4 gigahertz detector. This is a 866 megahertz charge span. And as you can see here, as you increase the number of tones, the voltage goes up. And the same here. But here I use also 64 tones. And what you see is the 64 tones come down. So 16 tones go up, 64 comes down. Why this happens? Well, because if you have a lot of tones, the peak is so huge, and the peak, as you saw here, let me go back, you see you have a positive peak, negative peak, and if you see this, the negative peak will go to breakdown. And if it goes to breakdown, this will decrease your efficiency. because you'll be destroying your waveform signal in the breakdown. So the number of tones is also an important thing. You cannot use 1,000 tones. You have to use the number of tones that allows you to go near the breakdown, but not going to the breakdown. Well, the other problem is that if I have one of these signals with these high peaks, I cannot send it via one amplifier of the transmitter, because if I do that, I will degrade the DC to RF efficiency on the transmitter side. So we come up with an idea of, instead of using one source and one single amplifier, we actually start to use different sources and you amplify each one of these sources individually. So when we transmit, each antenna will transmit only one signal. But when you combine them all, you have a whole design. So we actually developed this with some colleagues from CTTC, and actually the solution at that time was mainly to use four oscillators to show up. These are actually multi-locked oscillator arrays. So how this happens, we start an oscillator, then we start the second oscillator that couples to the first one, we start the third oscillator that couples to the other two, and we start the fourth oscillator that couples with the other three, so that you can create these peaks on the air interface, but not on each one of the antennas. So you don't have the clipping effect that you should have if you go with a four-tone towards a single amplifier. So, and as you can see here, we obtain a significantly efficiency gain over one-tone RF to DC converter. So this is the efficiency gain we achieve when we combine the four tones with multi-locked oscillators. Well, and just for you to remember, what was our initial objective? To increase the RF to DC efficiency so that we can power up a large array of sensors in our case, within a space environment, so for space exploration. So this concludes my talk today. I just want to tell you that we have a wireless power transfer journal. So if you want to publish your results in the wireless power transfer journal, please send us your paper. So the address is below here. And we created very recently the IEEE WPT. So the IEEE WPT is a small group of researchers from different areas that are bringing together their knowledge to, at this moment, a single website. And our objective is actually that we have the history of wireless power transmission there, we have standards there, we have the conferences being advised there. So everything related to wireless power transmission will be concentrated in that website. So thank you very much for listening, and I'm open for questions.